Somebody start a roll for me. All right, so by now I hope you've had a chance to log on to Mastering Physics. All right. So next week you're gonna start seeing your first assignments and all that kind of stuff pop up. So I hope everybody's situated and registered. All right. So it's 12 o'clock. So let's get started. All right. So on last time we spoke about, I think we did chapter 1, right? We did the lecture slides in chapter 1. And chapter 1, we started talking about science and theories and laws and all of that. And we ended up talking about motion, right? Motion. And in order to properly describe the motion or the speed of an object, we need two physical quantities, right? What are they? What two physical quantities do we need in order to describe the motion of any object? Yeah. Yes. Those are the two things. We need to know the distance covered, right? We need to know the distance covered, and we need to know how long it took to cover that distance. Okay? And so as we recall, that's the simple equation of what? Speed is equal to distance over time. Okay? So now we're going to see some more complicated equations as we get, particularly as we get in chapters 2 and 3, when we start talking about projectile motion, right? Like a football, throwing a football. It's different from dropping something, right? Equations get a little bit more complicated, okay? When the object moves as a projectile, okay? But we're going to start with one-dimensional motion, right? One-dimensional motion is what? Free fall. Motion in one direction. That's called one-dimensional motion. All right? Now, if I did this, that's motion in two directions. Which are they? Which directions did that, when I threw that marker, which motion, can you tell me in which direction was the motion occurring for that marker? Huh? Up and down and? Across. But they occurred at the same time. That's why it did this. Now, in free fall, what? It just does what? Or it just moves what? Up and down. So that's one-dimensional motion. Two-dimensional motion means we have motion on more than one axis. Okay? And of course, we can get more complicated when we talk about things like planets, right? Because how many motions does a planet have? Well, it has multiple, right? Because it's doing what? It's doing this around the sun, and it's spinning on its own axis. Okay? So, yes. So, we have to be specific when we start talking about motion. Like, what type of motion is it? That's very important because that's going to define which equations we use. Okay? So the first question is, and we'll start with something very straightforward, something very simple, right? Let's say you drove 320 kilometers in 4 hours. Okay? Oh, that's not a question. Calculate the speed, right? Can y'all see this? Y'all can see that pretty good? Let me see how it looks on the video. Yeah, I'm gonna have to get some better. Maybe I should use some colors. Well, I'll get some. I'm gonna buy some of these markers over the weekend. Calculate the speed. Right? Pretty straightforward, right? Yeah? What is it?
You would just do 320 over 4 hours.
320. Right? The distance we covered was what?
320 kilometers.
320 kilometers. And the time we covered it was what?
4 hours.
4 hours. So that's 80 kilometers per hour. Right? Pretty straightforward, right? So now, we calculated the speed. Now I'm going to say, well, express your answer in meters per second. So when we express in meters per second, what does that mean? What do we have to do? Conversions, right? We must convert 80 kilometers per hour to meters per second. So how are we going to do that?
Say 1,000 kilometers in a meter.
See, 1,000 kilometers in a meter. Huh? Yes. All right, but first let's start. So what we're gonna use? What's the method we're gonna use? What they call it? Conversion, T-chart. All right. And so let's y'all got this already, so let's erase this. Alright, and so we're gonna start with what? 80 kilometers over 1 hour. Right? And we're gonna extend this out like that. Right? And somebody said what? We're gonna deal with the kilometers first. Right? So what goes on top, what goes on the bottom? So 1 kilometer on the bottom, 1,000 meters on the top. Right? All right? Kilometers cancel, right? Now what? We need hours to what? Minutes? What we gonna write on top? 1 hour, 60 minutes, 1 minute, 60 seconds. All right. So when we cancel, when we make sure our everything's canceling out, hour, right? We left with what? Meters per second. So now I need to take care of the numbers, right? What's the number? $22 even?
Well, it's 22.22 because I don't know if you see it.
No.
So it's 22.2.
22.2? What?
Meters per second.
Meters per second. 22.2 meters per second. Anybody got anything different? Everybody got the same number. Okay, that's good. So we converted 80 kilometers per hour to meters per second. All right. So, so that was pretty straightforward, right? So now let's deal with a specific type of motion, right? Which we call free fall. Free fall, right? It's a very specific type of motion. What is specific? What is so unique about free fall? What about it? Yes, it's a motion with a constant acceleration.
Oh yeah, like the higher it is, the more speed, the higher speed gonna pick up.
Yes, indeed. The higher you are, meaning the more force that you will hit the ground with. Okay? And so there are certain equations that we use to describe this type of motion, right? And it's here, right? X, well, let's talk about Y. Let's talk about in the Y direction, because we're talking about, because, right, we could talk about in the Cartesian coordinate system, you have what? X and Y. Okay? We're talking about something falling in the Y direction. Okay? So we're going to call that Y. Y equals Y naught. What does naught mean? Naught means the initial. Initial. So the initial distance that the object covered before I dropped it was how much?
Good.
Nothing. So a lot of times, this is what? 0. A lot of times, but not every time. That's why it has to be there. Most cases it's 0, but sometimes it's not. So they just put it there. But in most cases it's 0. All right? Y naught plus V, right, times T. Okay? V stands for what? Velocity. All right? Velocity. All right, so Y is distance. Y is distance covered. Y naught is initial distance covered, which is a lot of times 0, but not every time. And I'll write that, which is oftentimes 0, which makes your life a lot easier, right?
Are you saying not as in like NOT?
Not as in the 0 subscript.
Right, but like,
NOT, not, yes, not, yeah. Whenever you see a 0 subscript, that's not. That's a universal thing. Anywhere you go, from here on out to grad school, anything. Somebody says not, they mean Y sub 0. The initial. Okay. So V is what? And V sub T, right? Actually, that's not V sub T, that's actually V times T. So that's V. So actually, right? So this is V times T, not V of T. Okay, but V, let's just write this here, right? V is what? Velocity, right? Velocity. Okay?
But they're saying the first parentheses,
oftentimes 0.
which is
Which is oftentimes 0. Plus what? 1/2 GT squared. Right? So G is what? G is what? Huh? Grams? Gravity. Well, I mean, what are we talking about, y'all? I thought y'all was gonna get that one. Y'all was gonna come up with that one. All right. Yeah. We not. I know you just came from chemistry class, but we in physics. We deal with grams too, but not just yet. G is for gravity. All right. And obviously T is for what? Time.
So both of those T's are time?
Yes. Yes, because this is a quadratic equation. Yes, both of these T's are time. Right? So now the question is, how far does an object travel in free fall after 3.9 seconds? That's a question. How far does an object travel in free fall after 3.9 seconds? So which equation we're going to use, right? Well, obviously we're going to use this equation, right? But eventually you're going to have a nice swath of equations. And you're going to have to know which one you need to use and when. And so that requires practice, right? If you practice it enough, then you'll get accustomed to which equations are useful in which situations and which are not. Okay? So obviously we're going to use the free fall equation to calculate the distance. How far? When it says how far, they're asking for what? A distance. How far? They didn't say how long, so my answer can be in seconds. Right? Y'all follow me? All right. So then what we said we're gonna use this equation, so let's do it. Right? So y is obviously what we're looking for, right? Because y is what? The distance covered. That's what we're calculating. It said how far does an object travel in free fall? So we're calculating y. So what is the initial distance before I dropped it? 0. That takes care of that term. Okay? At the moment I drop an object, the very moment I drop it, or the very moment I let it go, how fast is it traveling? What's the obvious answer? The very moment I let it go. Let y'all think about that.
1 second.
Huh?
1.
No.
0.1
No.
second. 0.5 second.
No.
Now I'm just
What's the yeah, you just guessing now. What's the obvious though? What makes life so easy in mathematics? When if I'm holding something and I drop it, there is a moment in time where it's what? Huh? Yes. Before gravity does what? Accelerates it. I like that. Right? You got to use the right terms. Before gravity accelerates the marker towards the earth, it was in the air for a moment in time and it wasn't moving at all. Right?
That you like you standing on top of a building, you drop a penny down.
For a moment, that penny is not moving until gravity says, phew. Right? Just like if I throw something up in the air, what's going to happen? It got to come back down. But when it reaches the top of where it's going to go, what does it do? No. Hit 0. Because it has to hit 0, then do what? Turn around and come back down. But it got to hit 0. If you running and you want to turn and go the other way, what you got to do?
Turn around.
No. You got to stop. That's very important. See, we don't think in these are the laws that govern the universe, right? So we talk in colloquials, right? Like you say, oh yeah, if I want to turn around, you gotta turn around. If you was running full speed and turn around, what'll happen? You're gonna fall, you're gonna hurt yourself. You gotta stop first. So that means what? V is what? 0. So anything times 0 is what? 0. That takes care of that term. Right? So now I'm left with what? Y equals what? 1/2 GT squared. That's my equation for free fall. And of course, if I go back, I look at my problem, then I have what? 1/2 times what? G is what? 0. No, G is not 0. Gravity. What is the number? 9.8. So the acceleration due to gravity, and we must commit this to memory, meters per second squared. 9.8 meters per second squared. That is something you just commit to memory. That is the acceleration due to gravity. So that's what you're gonna put. I call it A. It could also be called G. Sorry, some of y'all was looking crazy, so I might have confused you. Right? It's G. G is just another form of acceleration, but it's gravity. So then I do what? I just plug and chug it, right? 9.8 meters per second squared, and then what? 3.9 seconds, right? And square that. What's that answer? And I need to get an answer from 2 people, and y'all need to agree before we can move on.
About 74.53.
You said you got what?
74.53.
74.53. What? Meters. That's the unit of length we're using, right? Anybody got something different? So what does that say? That says that what?
Or the object travels after 3.9 seconds.
Yes. Right? And that's very important, right? After we calculate, after we do a problem and we get a result, we need to say it out loud to ourselves. That helps with understanding. Right? So what we would do is say what? The object here under free fall travels 74.53 meters in 3.9 seconds. So what that does is, when you say that to yourself, right? If you calculated something that don't make sense, then you're gonna be like, I dropped the object. Let's say for instance, you calculate, somebody asked for how long does it take the object to hit the ground when I dropped it from 74.53 meters. Okay? Let's just assume you didn't know, right? But you've already calculated a number of different problems, and you see that somewhere around 75 meters, it takes you about 4 seconds. So what if you calculate 40 seconds? Then what you do? What you know? It's wrong. It doesn't make sense. It's not reasonable, right? Based on what I've done in the past. Like I say, we don't make this stuff up. I'm not making this up. This is what happens in the real world. If we go drop an object off this building, go on top of the building and drop an object, after 3.9 seconds, it's going to travel 74.53 meters. And you can measure that. Yes. If I was doing y'all lab, we'll do a lab and I'll show it to you. But I don't think I'm doing your labs. Right? And by the way, everybody got a lab in here, right? Everybody got a lab teacher. Okay. Good. No? Well, what you doing then?
I'm trying to get override now.
For what?
For the lab.
For whose lab?
Rubio?
Okay. You talked to him already?
Yeah.
All right. So yeah, so that's free fall. That's free fall. That's a very specific type of motion, right? 30. Okay. And so yeah, so that was one problem, y'all, right? No, we did one problem or 2? I think we did 2. Yeah, we did 2. All right. So I know I move a little bit faster in this class, right? Cause y'all are the science people, okay? But right? If we was in physics or something like that, then we need to be making solving 4 and 5 problems each class, right? So the reason being is because when we get on the exam, right, you're only gonna have a certain amount of time, and you need to get through, especially conversions, right? Because a conversion may be something that you got to get the right answer first, then convert it. So if you get the wrong answer and then convert it, both of them wrong. Follow what I'm saying? So, so we need to get the right answer, and then conversion needs to be like a second-hand thing to us, right? That we always get conversions right. We just need to get the right answer here. Okay? All right. So that was free fall. So let's deal with something else. Okay? That was a free fall equation. Oh. All right, so there's another equation we call the golden rule. Called the golden rule. All right? This is called the golden rule. All right? For Newtonian mechanics. For Newtonian mechanics. All right? And the golden rule just says that the final speed of an object squared minus the initial speed of an object squared equals to 2 times the acceleration of that object and times the distance it covers.
That's mechanics.
Yes. Mechanics. Anybody know what mechanics means? Huh? No? Huh? Yes. Things that move. Right? When your car breaks down, who you gonna call? The mechanic. Okay?
Is that A just like gravity?
Yeah. Well, it can be, depending on which direction we're talking about. Up and down, yes, that is what it is. Right? But when we're moving from side to side, gravity doesn't affect things this way. Okay? So not only do you have one-dimensional motion in terms of free fall, but if I walk straight like this, and then just stop, I just moved in one dimension, right? I walked this way, I covered a distance, and it took me a time to cover it. So I had an acceleration as well, right? It wasn't gravity though. Gravity didn't make me walk from here to there. I did that, right? Gravity will make you do what? Smash into the earth though. Okay, so it's the golden rule, right? So let's talk about the terms. Okay, so V sub F stands for final velocity. Final velocity. Why is that important? Final velocity. Why is that important? So an object can have more than one speed, right? It can move you can be driving, you can be going home driving at 40 miles an hour and it start raining and you say, I'm gonna slow down to 35 because it's wet. In that case, you had two different speeds. So we need to specify which was your initial and what was your final. So V sub naught is obviously what? Initial velocity. How fast you started out and how fast you ended up. That's important. All right. And A stands for acceleration. Like my man said, it could be gravity too, depending on if we're talking about up and down or we're talking about side. Well, if we side to side, then we call it A, acceleration. But when it's up and down, we call it G. All right? That's going to be important. And you're going to see in chapter 3 when we start talking about vectors. Okay? And we separate motion in the x direction and motion in the y direction. We separate those out and then we bring them back together to get a complete answer. Okay? And we're going to do that, right? So acceleration here, acceleration, and x of f is what? Final what? What does x stand for? Distance. Final distance. Distance. X of naught is initial distance. And remember, initial distance is oftentimes what? 0. Oftentimes it's 0. Just like your initial speed can be what? 0. When a plane takes off, it starts off from what speed? 0. When you're sitting there waiting, taxiing on the runway, it says 0. You ain't going nowhere, right? So this can often be 0 as well, but not always. There are instances where your initial speed is not 0, right? Like if I'm on a train, then my initial speed, if I'm on a train, I get up and I start running, then I have a motion, right? But is that motion only dictated by how fast I run? How fast the train moving too. Okay. So all right. So let's think about a problem, right, or a situation, and we're gonna be this one. We're gonna wrap up after this one, right? So this is the golden rule. So I don't want y'all to. So when we see, I'm big on language. All right. I use these terms all the time, and when I use them, I expect you to know them, especially if we've used them in class over and over again. We recorded the videos. You have access to the videos to go back and watch. So you shouldn't miss this. Okay? That's the point of me doing this. That's why I do this. All right? Record every lecture. Just like they do at the big schools. Right? So you ain't got no excuse. Even if you miss class. You can't make it today, that's fine. It's recorded for you. I don't care if you're here or not. This is not high school. I don't care. All right? So, if I asked you, I say, all right, well, a airplane, calculate the distance the distance of a runway needed for a plane to take off at let me get a real speed on the plane, because that's important, right? Because if you make stuff up, it might not come out. It might not make no sense when you do it. All right. Let me see something right quick. Don. Oh shucks. All right. Oh, here we go. I got one right here. Oh no. Let me see. I don't want to make nothing up real quick. Somebody Google for me how fast does a plane need to how fast does a plane, you know what I'm trying to say, before it takes off. Google that for me real make up a number and then it'll come out all weird. $150 to $180. Okay. Huh? It don't matter because we can do what? Convert it. It don't matter. All right. So take off at you said 150 miles per hour, right? Right. So the first thing we're gonna do here, right, is because we're at miles per hour, we got to convert it, right? So in this case, actually, yeah, that was a good question. Actually, so we can save time. What is it in meters per second? Do they get that to you in Google? And we save a lot of time that way. Kilometers per second?
Per hour.
What's that? Yeah, I need it meters per second. That way we don't have to do 75 meters per second. To take off at 75 meters per second. Okay? All right. So what we're trying to do is we're trying to calculate what? What are we trying to calculate? A distance. See, this is important. This is important steps, right, in problem solving. I'm showing you, and we're gonna go through in chapter 3 or something. They got a list of slides where we go through the steps of how you solve word problems. Because I know a lot of us, right, when we graduated high school and we've been, in college a couple of years, and we might not have done any word problems in a few semesters. Okay, so yeah, so we calculate distance. That's the first thing. That's the first step you need to do. You need to know what it is you're calculating, and remember that, because a lot of times these things have 3 and 4 and 5 calculations, and you can easily forget what you needed to end up with. So we're looking for distance. So what's here is distance. X. So then I need to rearrange this equation for x. Or at least what xf minus x naught. But we said x naught is typically what? 0. So we could just say xf. So xf, or we could say xf minus 0. That's the same thing as xf. Right? So xf is equal to what? I just bring the 2a, divide 2a by both sides. 2a cancels on that side. I'm left with what? V final squared minus V initial squared. All of that over 2a.
The 2A not negative.
Huh?
It's not gonna be negative. It's on the same side.
Well, we divided, right? We divided it. We divided it here. That's why it went away here. And then we divided on this side. And that's why it's showing up right there. Okay? So, now we have an equation for distance of our runway. Right? Oh, and calculate the distance of a runway needed for a plane to take off at 75 meters per second, accelerating. Google, what's the acceleration of a plane in meters per second? That way I don't make up nothing. Okay. Accelerating at 2 meters per second squared. Forgot to add that. All right, so if I came here, boom, right? So what's my final velocity? 75 meters per second. What is my initial velocity? 0 meters per second, because we started off taxiing on the runway, right? And then 2 times what? 2 meters per second squared. Okay, and these are squared, right? So if we square 75, we get what? 225? That's the square of 75? No.
5,625.
5,625? Yeah? Okay. And if I square meters over seconds, I'm going to get meters squared over seconds squared. Then divide that by what? 4 meters over seconds squared, right? And when I divide these out, I should end up with meters, right? Because these seconds squared is going to cancel, and that's going to cancel with that. I'm going to end up with meters, right? What's the number? 200 and something meters?
It's
1,000?
yeah.
Oh, yeah.
1,406.
1,406 meters. Now let's convert that to feet.
It's 1,406.
1,406. 1,406. Now convert that to feet. Everybody sign the roll. Where is it? Huh?
I got 4,612.
Anybody else? Okay. Nobody else?
I got 4,612.
4,000 what?
612.
612. So, is that the same thing you had? So I'm guessing that. So let's assume that's right. 4,612 feet, and let's do that to miles. So 5,280 feet, 1 mile. So divide that by 5,280.
1,872.
So a runway needs to be about 1 mile long. Right?
Yeah.
I mean, you're agreeing with me, but is that what you understanding here?
Right.
Okay? Don't just say yeah, right? Because, that don't help you now, right? Because you're relying on me, right? But when you get on the exams, right, you got to be able to look at this and say, okay, a runway shouldn't. What if I calculated? What if I did this and it came out to 52 miles? Then you know it's wrong. You know a runway cannot be 52 miles. That's ridiculous. You've been to the airport. You've seen the airport. A runway is not 52 miles long. Okay? All right, y'all. So on Monday, I'm probably going to start uploading to Mastering. So everybody needs to be registered and in the software, okay? I would recommend that you download your book so we can hit the ground running on Monday, and we might just jump to the next chapter so we can catch up. We missed that week for the snowstorm, so we need to catch up some. Well, all right. Have a good weekend. Maybe I should. I don't know if I could, but maybe I'll just do that and let it capture that. Maybe did it capture the entire calculation? There we go. And I'll leave that right there for a few minutes.